Good evening, everyone. Welcome back to MCL Live session. And today we are going to discuss about the basic concepts that have been covered in the week 9 session. The session was about to happen on Saturday, but we have preponed it. Sorry for the inconvenience caused to any of you. So shortly we will start the session. And what are the topics that we are going to discuss today is mostly surrounding the polymers, different types of materials over there, and their properties. So if you have any other doubt besides the today's session, please feel free to ask or put the question in the chat box. And at the end, we will be solving some assignment questions. So that would be helpful for you for solving all the assignment questions that are already uploaded. Yeah. So without wasting any further time, today's session is about the topics that we are going to cover. We will be talking about, we have already discussed the different types of polymer materials, thermoplastic, duroplastic, and elastomers in the last session. And today in that distinction itself, we'll be talking about further two more classifications, which is plastoplastic and reversible duroplast. Followed by it, we will be having classification of polyethylene on the basis of density. Then we will be talking about polymer classification, which is having condensation polymerization, addition polymerization, step growth, and chain growth. Different types of different ways of synthesizing the polymer, different processes that are involved with their examples. We will be discussing in these four topics, which is very, very important. And after that, we will be uh, in continuation of that, we will be talking about fillet process. And then the last topic would be our of reaction. So these are the topics that we are going to discuss today. More of the learning portion, not having much mechanisms involved. So let's start our first topic, which is okay. So earlier we saw that polymers that we have classified depending upon their segment mobility and the kind of linkages is there. So we have already seen the thermoplastic. That was the first type that we discussed last time. Thermoplastics, they don't have any memory. Once they are deformed, they cannot come back to their original shape. They have low segment mobility. Just a recap. Second, we saw the duroplastic materials. They are also not having much memory and they are rarely crystalline and they have the least segment mobility. And the third type that we have discussed in previous sessions is the elastomers, which are having memory effect. So you have applied the force on a material, it has been deformed. As soon as the force is being removed, the shape is retained. So it remembers the shape and it is having high segment mobility. Depending on what kind of cross linkages is there. So this we have read in earlier session. Now today what we are going to talk about is the fourth type is elastoplastic material, which are also known as thermoplastic. So from the name itself, there are certain features that we want to highlight. It's that they lie in between non-cross-linking. We know that in thermoplastic, we don't have a cross-linking thermoplastics, and elastomers are cross-linked. So it's a combination of these two. Whatever the materials which lie in between the two and having the properties of them, they're called elastoplastic or thermoplastic. Second is they are achieved in copolymers or in blends that have both duroplastic and elastomeric domains. So either they will be achieved in copolymers or when they have been blend having the characteristics of both duroplastic as well as elastomeric domains are there, followed by it has been seen that at low temperature, mechanical properties of elastomers they dominate, and at high temperature, material becomes thermoplastic. Why is it so? Because the cross links of the duroplastic domains they will cleave. So when we have a material, this kind of material, and at low temperature, elastomers property would dominate, and at high temperature, the cross linking between the material that would cleave, and therefore it becomes a thermoplastic. So this is sorry, this is all about the elastoplastic materials, which are also called as thermoplastic. Now we have fifth type is reversible duroplast. So as their name suggests, they will be having properties of both duroplastic and thermoplastic. Generally, duroplastics are irreversible. They are irreversible, whereas these are reversible, as the name suggests itself. So the kind of bonding that exists in this one is a coordination bond that is cross-linking arise from coordination of the ionic polymers to the methyl ion. The bonding is not covalent bonding, it's a kind of uh, coordination bond. Also, it includes partially crystalline thermoplastic material that also comes in this category, and also reversible, and also it has been found that reversible physical cross-linking that we were talking about that gets effective that gets affected by the lattice energy of your crystalline domain. Okay, so here we have the five particular types where the name itself is talking, telling you about what are the properties that are there in the five categories. Now moving to different classifications. Classifications of polyethylene based on density. And this also arrive from two factors. One is how much crystallinity is there, and number and nature of the cross-linking present. So these are the two factors on which your density is dependent. And based on that density, we have mainly three classifications, which is low density polyethylene, linear low density polyethylene, and is highest density polyethylene. So we'll take one by one. So the first is low density polyethylene. So sorry, the features of low density polyethylene is they are flexible, they are transparent, just like a film. Their density lies in between 0.902 to 0.925 gram per ml, and they have long chains with small branches. They would be branching in the long chains. So that is about your LDPE. Your second type is linear low density polyethylene, and here compared to that one, they are also really flexible and transparent. Their density lies in between 0.925 to 0.94 gram per ml. And they have branches on the main chain itself, where the branches were on small, uh, long chains with small branches are there, but in the main chain itself, they are having the branches. And the last type is high density polyethylene. As the name suggests, it needs to have the density from 0.94 to 0.97 gram per ml, and comparative to low density and linear low density, they are rigid, they have more density, and they are cloudy to opaque. They are not transparent or translucent, and they are just linear polymer chain without any branching. So I guess it is clear now. We can easily summarize that we have LDPE, we have LLDPE, we have high HDPE. This one is flexible. This is also flexible, and this is rigid. This is transparent. It is also transparent. This is opaque. Here it is having long chain with small branches. It is having branches on main chain, no branching. And obviously the density, we know the range 0.9 to 0.925, 0.925 to 0.94, 0.94 to 0.97. So this is the way we can so this is the way we can simply make a distinction between these three particular. So it's first type, second, and third. So it's very straightforward to remember. Not much you have to do about it. Now we will move to our next topic, which is the polymer classification. So in polymer classification, we first have the condensation polymers, the process through which they are being formed. So in condensation polymers, what happens? We have polyfunctional monomers, and after condensation, which undergo condensation, and we know this reaction gives the or eliminates some side small molecules. Say, for example, water, ammonia, etc. The example that we have here is if I am starting with this amine chain, where R could be any number. So it's one isomer, and another I'm taking a carboxylic acid with any chain number, and after the condensation it will form H, NHR, NHCO. This is your amide bond. R dash CO OH. This is your chain. So here if you will see, right, this is your monomer A, this is your monomer B. Both are functional, so we have the polyfunctional thing. Now after condensation, the if NH is like this way, and we have OH and C double bond O, so this will combine to lose the water, and therefore we get NHCO like this way, right? So this is your sorry, condensation polymer. And the best example that we know for condensation polymers is nylon separation. So nylon 6 is actually being prepared from this monomer, and which has the NHCO bond, and nylon 6 that we have comes from the diamine hexane. You have NH2, CH2, 6, NH2, and adipic acid. That is also a 6 number chain. So this way, these are the condensation polymers example. So what we were saying that there is another example. If we are taking diols plus diacids, and we know that if we have OH, say R, or this is any number, and we have the R dash COOH. Again, here the condensation would be the loss of water, and it would give you polyesters as your product. And if you want to form a polycarbonate, that also polycarbonates can be made as follows. We are taking diol, R is any number of carbon, plus you are taking Cl, double bond O, your phosphine, or acid fluoride, diacid fluoride. And here also you will use HCl and 2 N minus HCl, and you will get HO, this phenyl group, R group, and O, C double bond O, and there would be Cl at the end, right? So we got to know, we can just say that if we want polyamides, that means NHC double bond O group, we need to have diamines plus diacid combination, and the lost product would be H2O. If you want polyesters, which is OC double bond O R dash. So here we need diols plus diacid. Here also water is the small molecule which is going to be come out. And if we want polycarbonate, which is also R O C double bond O, and several examples here. So this you can get it from diols plus acid chloride, and the side product would be your HCl. So this is about your classification of the condensation polymers. Now we will move to the next type, which is the addition polymers. So addition polymers is just the addition of the polymers with no loss of small molecule. Okay. So here the repeating unit, that monomer, is having the same composition as that of your starting monomer. For example, polyethylene monomer is ethylene only. So that is your repeating unit, that is your starting unit. So it doesn't require two different monomers, it's only the type A. Now we are moving to our third classification, which is step growth polymers. Name itself suggests what is happening here. So it proceeds like a stepwise reaction between the monomers. Between the function groups of the reactants. So reaction actually proceeds in multiple steps. It's not a single step, it's a step growth. So it will occur in different multiple steps. Like we will be having monomer plus monomer. It would give you dimer. When dimer reacts with monomer, it would give you trimer. When trimer reacts with monomer, it gives you tetramer, and so on, so forth. So it goes in steps. It does not randomly take up. And when two high numbers are combined together, then the molecular weight would be more. So the molecular weight of the polymers, how it behaves from the 0 to 100% conversion rate, percentage conversion. Since it's a stepwise step growth, so it would be constant at a certain point, and at certain rate, it would shoot up the molecular weight, because there we can have a combination of two big uh, number change. So this is the conversion percentage conversion and the molecular weight plot for step growth. And if we have the fourth one as chain growth, so that means now we don't have the steps over there. It is a chain thing. So it just propagates. So this is important because it actually requires an initiator to start your reaction. Initiator means it has to initiate the reaction from which is produced as initiator species, this R dash with a reactive center. and then the chain growth occurs. Firstly, we need certain initiator to activate our reactant, makes it as an initiator species, and then it will continue to grow. Okay. So what we were saying that chain growth polymerization that requires an initiator to create an initiator species with a reactive center, and that can continue the growth. And here the polymerization occurs by propagation of the reactive center by successive addition of large number of monomers, a chain reaction. So say for example, I have this initiator species where the active center is this one. Now I have this monomer. This is my monomer, and this will go and tag here. Now the chain has been increased. Now again, I have another monomer. So further the chain would be increased to a new group, and it would continue to grow like a chain thing. So therefore, so this large number of monomers additions that happen so fast that the polymer molecular weight is actually independent of the conversion percentage because it remains constant throughout. It's the maximum thing. So it achieved its molecular weight at 0% or 100%. So addition is so fast. Therefore, it is constant. I hope you have understood. Talking about one more thing, if we see the molecular weight, polymer molecular weight with respect to the conversion, like a linear growth. So this linear growth is observed in biological systems of protein molecules, which is in fact having a polymeric chain, and this is called living polymerization. This is also important. Now we are heading towards the different processes, the two main processes, Philip and the off-core reaction. Since we have talked about the polyethylene, the low density polyethylene, high density, and the linear low density polyethylene, it has been found that earlier the LD LDPE. It used to be synthesized by ICI, which is empirical. It's an industry name, chemical industries, in 1933. And the ethylene is polymerized under extremely high pressures of less than 2,800 bars and high temperatures less than 275 degrees Celsius in presence of radical initiators such as oxygen with percentage 0.05 or peroxo compound. But the limitations of this is, firstly, we are producing LDPE, which is having low density and poor crystal salinity, and it would be having long side chain branching. These all things we have already learned earlier, and this requires synthesis requires extremely high pressures, less than 2800 bars, and high temperatures less than equals to 275 degrees. So that is the limitation with LDPE. Then later, heterogeneous catalysis comes into picture. Introduced by Philip and therefore called as Philip process in 1956, which produces high density polyethylenes that too at extremely low pressures of 10 to 30 bars, and they used the pre-catalyst as chromium oxide on silicon oxide and Al2O3 as support. So this is the thing, earlier version of this. Now if we have to produce LDPE, it is coming at an expense of high pressures and temperatures. So heterogeneous catalysis, calling it as Philip power, that has the tendency to produce high density polyethylenes at extremely low pressures and using the catalyst over there. So let's understand what is the Philip process. So the Philip processes we said we have silicon oxide uh, support on which CrO3 would act as a catalyst, and this is a support on Al2O3 also. Now we have chromium oxide, and since we have this chromium oxide and OH with the loss of water, it would form the structure. This is in +6, and here it would be CrO double bond O double bond O. It is still in +6, and this maintains its support. Now followed by we are introducing NCH2 double one CH2, that is ethylene. Firstly, some of the ethylene will get oxidized to give you the formaldehyde, and chromium gets reduced to form chromium, oxygen, silicon, oxygen, and here it would be in fine fractions with the 2-ethylene. Now it is reduced to +2. It is in +2. because your ethylene got oxidized, some of the ethylene got oxidized and chromium got reduced. It can be rearranged to form this chromium five-membered methyl cycle structure. So here it would form this CH2, 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 and CH2. This is alpha, alpha hydrogen, and this is beta hydrogen. Now, once it attacks on this, here the chain opens, and again we are having chromium hydride bond, oxygen, and oxygen, silicon. This is the support, and your chain has now been opened, making a double bond over here. So this is your chromium hydride species, which on treatment with N times ethylene molecule, it would undergo forming. Now this would become as CH2, CH2 a polyethylene chain with edge outside, and the other one would work as an allylic group, oxygen, silicon, oxygen, silicon, and this is your chromium 3. So here you got your product. Similarly, later on, some catalyst variation by union carbide, they employed instead of they employed chromosine CP2CR, and here we have a low valence chromium in +2 oxidation state. The procedure remains the same, where if we have silicon OH, OH, now when it is treated with hydrogen and chromosine, each CP group gives you -1 charge, therefore chromium is +2. On hydrogenating the species, one of the species takes the hydrogen and give you C5H6. One hydrogen goes with the chromium, made a chromium hydride bond. The CP remains intact, and this +2 now goes to 4, and ultimately on treatment with ethylene, it would give you chromium CP group, and this hydride can easily be transferred to this species, making it a polyethylene, oxygen, oxygen, and silicon, oxygen, silicon. So this is your product which can be formed using the chromosine. Now the last part of the lecture is of a reaction. So it is being used to give for the formation of linear aliphatic compounds. So here how the reaction goes. You have R2Al C2H5 and N minus CH2 ethylene group. Now Under these conditions, 90 to 120 degrees Celsius and 100 bars, what it will do is it would convert your C2H6H5 into CH2, CH2, N, H. So this is the long chain we can observe. Also, sometimes this off-par reaction competes with the dehydro elimination. And what is that? Dehydro elimination means if we have R2Al, since the chain that we have taken are, this is alpha, this is beta, and this would give you hydride plus CH2 double bond CHR dash. This is called the elimination. During the systematic study of per process, Ziegler observed a reverse or opposing effect, that is from C2H4 to ethylene, it is converting to 1-butene, and later it was found that because of presence of nickel impurities in the reactor where the reaction was happening, so therefore it was called as nickel effect. So with that, our concepts for the week 9 has been covered, where we have seen the two other classifications of the polymer. The further we have seen the classification of polyethylene based on the density. We have seen the classification of polymer based on the processes, condensation, addition, step growth, chain growth. Then how it is being formed industrially, and we talked about the filler process, we talked about the offer process, and also we saw the nickel effect. Now we will use these concepts for solving the assignment. So here the first question says that the increasing order of segmental mobility in thermoplastic 1, duroplastic, and elastomers. We have already explained that elastomers are having the maximum, third is having maximum compared to duroplastic. Thermoplastics are having more, and duroplastics are having the least one. So the right option is your C. Now we have the elastoplastic materials that exhibits the hybrid properties of what? We already know that elasto means it is coming from elastomers, and plastic comes from your thermoplastic, and it is having the properties of both. At low temperature, elastomers would exist. At high temperature, because of the breaking of cross-linking, it would form thermoplasts. The option B is right. Now, the typical molar masses of HDPE using the Ziegler-Natta catalyst, it's actually the range, we have to know it, that it's less than 3 into 10 power 5 dpi. Now, the correct order of density in these three, we know that these are the classification of polyethylene based on the density. As the name suggests, it's low density. Then linear DPE is little higher compared to this one, and HDPE is the maximum. So we have the HD, so it's the right, the option is the right one. HDPE is the more. Then density we also know it's 0.94 to 0.97. This is 0.925 to 0.94. This is 0.9 to 0.925. Also, now we know that Philip processed produces HDPE because there was a limitation with the LDPE. So it has produced a HDPE that too at low pressures. In the filler process for the production of HDPE, the catalytic active species we have already talked about. It was chromium in plus two, where actually we start with chromium in plus six, and then it goes in a conversion to make an active species of chromium in plus two, where it is connected with your ethylene molecules. The seventh question is the monomers of nylon 6. I've already told. Don't get confused. The nylon 6 is this one, which comes from this monomer, which is the caprolactam. And these two, the adipic acid and the hexa methyl diamines, they form nylon 6,6. So don't get confused. The nickel effect, we have already seen that nickel effect we have seen in the Aufbau reaction, where in presence of the nickel, ethylene is giving you 1 butene. So this is from your Aufbau process. Now, the polymer molecular weight increases drastically at higher percentage conversion. So we know that for step thing, we at higher rate, it was near to 100%, it goes immediately. For chain growth, it is constant throughout because it will not change. It will be doing very faster. And living polymerization, that's a linear thing. So the answer is here. Sorry, it has been asked that drastically changes at high percentage conversion. So it's a step polymerization. And the polyethylene polymerization process that is carried out in fluid bed reactor is called as unipole process. So with that, our assignment questions are over. If you guys have any question, please feel free to unmute yourself and ask the question. I'll be happy to answer. Okay, so am I audible to you? If I'm audible to you, please give a reaction to it, either thumbs up or okay. So the topics that we have covered today are shown over here. We have actually talked about the different materials. There are certain types. Last time we talked about thermoplastic, duroplastics, and elastomers. The two other types of the polymeric materials, they are elastoplastic and reversible duroplast. So we have generally talked about their properties. And today there was not much mechanism, but yes, we have taken all the topics which have been covered in week 9, say for example, polyethylene classification based on the density. Based on the density, we have three main classifications, which is low density polyethylene, linear low density polyethylene, and high density polyethylene. And followed by, we have talked about polymer classification. That means the process which has been used to make polymers, say for example, condensation polymer, the addition polymer, step growth, and chain growth. So I'll just give you a little glimpse what we have discussed so far. Give me a minute. Sorry. Okay. So where are we? So here I'll just give you a brief of it because the session actually started at 6, so we are almost about the end of it. And at last, we, after discussing all the things, we talked about the Philip process and off-pour process. So basically, the questions would come to know from the different properties that they have. For example, the thermoplastic main property they have is that they don't have a memory. Say, for example, if you have applied a force and after force for certain time, if you'll remove the force, once the that material has been deformed, that will not come back to its original state. The plastics, if for example, if they are melted, they cannot take their own form back again, and they have slow segment mobility because there is less cross-linking also. So then we have a duroplastic. Duroplastic has rare crystal nature and very less mobility over there. And elastomers are the one which are having more memory. Say, for example, if I'm applying force onto a material and if I've removed the force, still it is maintaining and remembering its early stage, like the way it was. That is called the memory effect, and elastomers are having. So this we have learned in the last session. But today's session, the two further types of polymeric materials were elastoplastic, which is a combination of elastomers and thermoplastics. And at low temperature, your elastomers would appear, and at high temperatures, the cross-linking of the monomers would break, and you will get a thermoplastic. So it is having a combination of both the materials. Further, we were having last type is reversible duroplast, which is having the properties of both duroplastics and thermoplastics. So if you know the first three types, you can get to know about the other two combinations as well. So the main difference between the duroplastics and these reversible duroplastics, it's all about the reversibility, whether they can go back to their mono forms or not. And mainly reversible duroplasts, they are having a bonding nature as a coordination bond. They are not having a covalent bond over there. It's just a metal and the ionic nature of the linkers that we are using. After that, what we discussed about is the polyethylene classification based on the density. We also know that density is mainly dependent on the how much the material is crystalline, and second, how much what is the number and the nature of the cross-linking present over there. And based on that, we have the linear low density polyethylene, linear low density, and high density. So I'll just go to the summary quickly. Uh, this is the summary. Low density polyethylene is they are flexible in nature. Similarly, the linear ones are also flexible, but the high density, since it is high density, so that's why they are rigid. Both the first and second type they are transparent in nature, but the third one is opaque in nature. LDPE is generally having a long chain which is having small branches. So you can just consider any polymeric chain and which is having a small branch over there. Whereas your linear low DPE would be having the branches on the main chain. That would not be having the small branches, but it would be having directly onto the main chain. Whereas high density polyethylene would be having no branching. And their names suggest their names are coming directly from the density values. If you can see, the LDPE range of the density lies from 0.9 to 0.925. If we go from 0.925 to 9.94 and 9.94 to 97, that is high density polyethylene. Further, then we saw that how we can classify our polymers. So these are basically the classification of polymers or different grounds. Say, for example, firstly, we were talking about their physical properties, then we got thermoplastics and elastomers and so on and so forth. Secondly, we saw based on their density. And now we are talking about the process that they are undergoing. The first type is condensation polymer. Condensation itself realizes that we are taking two different monomers. They are condensing together. Whenever the condensation happens, there would be a loss of some molecules because the entropy also increases. Say, for example, I have this diamine system and we have a diacid system. So when we know that amine and acid reacts, they would make an amide bond. So NH double bond. How it will form? The proton from the amine and the OH negative from the acid, they would combine together to give you water. So this kind of elimination of small molecules happens only in the condensation polymers. So they will give you a long polymeric chain with the defined group that you want. Similarly, if you want, these are the examples that we consider for the condensation, the nylon that we already know. If we are talking about the nylon 6, that comes from the caprolactam, and the nylon 6,6 is the combination of two different monomers. You can just go back and read some textbooks, whichever have been mentioned in the lectures by the professor, and you will get to know about different examples which undergo actually the condensation. And this I was talking about like polyamides if you need. If you need polyester, say for example, the ester group is nothing but the C double bond O and OR. So what you need to take, you need to take a diol and you need to take a diacid. Here also the small molecule which is going to be eliminated, that is water, and you will end up having a ester. Similarly, if you want to form a polycarbonate, so this is the process of having different kinds of polymers with different functional groups, how it is happening with the loss of small molecules, and that comes under the condensation polymer. So here polycarbonate, we are having a diols, and here we are using, instead of the acid, we are using the acid chloride. And this would lead you to form a carbonate, and this is the reaction between the diols and the acid dichloride. Now, this is the summary of it. And another type of the polymers based on the process that they're following is the addition polymers. In the condensation polymers, we saw that there are two different monomers. There is one monomer. Say, for example, if I want to make polyamide, then I need to have a monomer of amine and I need to have a monomer of acid. Whereas in case of addition polymers, there would be only one monomer with the same repeating unit. Say, for example, polyethylene. Polyethylene only requires the ethylene molecule. It does not require any other molecule and there won't be any loss of small molecules. So this is the addition polymer definition. Now, third type that we have is step growth polymers. Step growth polymers is the definition, the name itself suggests like what it means. Step growth means that it would go stepwise. It is not a direct process that we have mixed the two and we will be ending up having the highest molecular weight polymer. No. So what it will do, it goes step by step. We have taken one monomer. That one monomer is combining with another monomer. Sorry, it will give you the dimer. Now this dimer will combine with monomer to give you trimer, and correspondingly the chain increases. So what we see that this is the kind of graph depending upon the conversion percentage. Say for example 0%, matlab the reaction has not even started, and how much molecular weight we are expecting of the polymer. So it is just constant up to a certain time. Once it is reached up to a certain completion rate, it would immediately shoots up as the molecular weight increase, which is not there when we are talking about the chain growth polymers, because chain growth is irrespective of what is your conversion rate, it will give you the maximum molecular weight at first stage itself, because it's a very fast process. So in the chain growth, we have to follow up a radical kind of mechanism where we need a initiator. Say, for example, I have taken some initiator to make my monomer as a active species. Once this has been formed, then it would, just a second. Yeah. So once it is formed, say for example, using an initiator, this was my monomer. I have initiated this group, and this R star is symbolizing the active center where the other monomers are going to attack. So this blue one is my second monomer, which is coming and attacking on this one. It forms a long chain. Another second, third monomer will come and attack, and therefore the chain continues. And this chain actually being formed at the very first step itself, because it would be so fast that your conversion rate is not dependent. Your molecular weight is not dependent on the conversion rate. At the start of the reaction itself, the reaction is so fast that it will give you maximum molecular weight at the first step itself. That's where there's a difference between the step growth, which goes like progressively and shoots up the molecular weight at a certain conversion point. Whereas in case of the chain growth, it would be constant because it has already achieved the molecular weight, which is maximum. Now, there is one more example. If you see, we have seen the example where if it is something like constant and then shoots up the molecular weight, that is for your step growth. And the other one that we have seen, if it is constant throughout the conversion percentage, that is your chain growth. And if you see something, this linear chain, this linear line with respect to linear relationship between molecular weight and the percentage conversion that you see in case of the biological systems, because there it is actually depending, as in when your conversion is increasing, your molecular weight is increasing, and that comes under living polymerization. After that, so we discussed all the types of the polymers based on their process, based on their density, and the kind of physical properties that they are having. Now, how they have been made and what is the history behind it. So, in the week 9, that has been covered by the professor, and I've given a gist of it over here. So, earlier, there was an industry, empirical chemical industries, that used to synthesize the LDPE, which is a low density polyethylene. But today, these ethylenes are being polymerized at very high pressures. Look at the pressures; it's less than equals to 2800 bars, and temperatures are reaching approximately 275 degrees, which is very, very high. Whereas we realize that LDPE, which is low density polyethylene, they are having low density, they are having poor crystallinity, also they are having branching. So they have the limitations, and the synthesis requires a lot of pressures and temperatures. So after that, thinking about the limitation, one scientist came with the methodology where they used the heterogeneous catalysis called as Philip process, given by the Professor Philip only, that has turned the synthesis of the ethylene to the high density polyethylene, because this is high density molecule and it's having a high crystallinity also, which requires a pre-catalyst, which is chromium oxide, and it is on an active surface. Look at the main thing, which is a low pressure. Earlier we were using a pressure range up to 2800 bars, whereas in case of the high density polyethylene, using this Philip process, we could able to get the synthesis in just 10 to 30 bars, which was the achievement. And this is certain mechanism. As I said, we will be using a heterogeneous material. Heterogeneous catalyst works on the surface only. It's not a bulk process, it's a surface process. And here the dash line is actually showing you the surface property, where you have a silicon oxide, and in presence of your chromium oxide, which is your catalyst. And right now it's in plus 6 oxidation state, since we have an oxygen and OH over here. To make this cyclic product, it would go and release the water. And here again, the chromium is maintaining its plus 6 oxidation state because the 2 minus charge is coming from this oxo and 1 minus charge is coming from this oxide. Now, when I'm introducing the ethylene molecule, because generally, what is the main feature? That is the ethylene to be converted to a high density polyethylene. Now, when it has been introduced, since ethylene is coming into picture and it is already in higher oxidation state, to get connected with this one, firstly, this ethylene gets oxidized to formaldehyde and your chromium would get reduced to the lower oxidation state. So one species would get oxidized and other species would get reduced. So what would be the product? The other ethylene molecules, because we are using a lot of ethylenes, so that formaldehyde will go off and chromium will change its oxidation state to from plus 6 to plus 2. And this is your active species. So here, this is your active species, which is connected and coordinated with the ethylene as a pi interaction. And only the -1 charge is coming from this oxygen and this oxygen. Now, what will happen if it undergoes a rearrangement to form this 5-membered ring where the CH2, CH2s are combined together as a case of a metathesis reaction. So we know that the bond which is connected directly to the metal is known as alpha, adjacent to that is beta, and then gamma, and then delta. So this beta hydride elimination, we already know that hydride at the beta position, it's very, very reactive and it can easily cleave to form a double bond. So ultimately, we'll be having a chromium hydride and this double bond is formed over here. Once it is formed, it continues to react with your ethylene molecule and this would give you a chain over here. So therefore, we get a polyethylene with the high density at very low pressures if we use a Philip process. Considering this one, another industry called Union Carbide, they employed the chromosine. Earlier, we were using the chromium oxide. Here, the new catalysts were being introduced that was having a oxidation state of plus 2. And the similar process and mechanism was followed. Firstly, we have a silicon oxide support in presence of the hydrogen and the chromosine, which is your catalyst. It would convert to your chromium hydride, and on reaction with the ethylene, it would give you a polyethylene. So this was about the Philip process with two different catalyst versions. Now, the last topic of our today's topic was off-for reaction. So off-for reaction is nothing but if you want to get a very long chain with a maximum length of C20 or more than that, we are using this particular reaction where aluminium compound is being used and ethylene has been used. And under these reaction conditions, 90 to 120 degrees Celsius and 100 bars, you will be ending up having this long thing because there the C2H5 is there and CH2 is there. They would combine together to give you a long chain. But sometimes when we have this kind of moiety, because it would be having a beta hydride, so what would happen if it is having a beta hydride? It is this much fissile that it would create a aluminium hydride bond and would lead to form this particular chain, which is stopping at this level. It would not continue to form. So when it was being investigated by Ziegler, that why it is happening, why the ethylene is stopping at 1-butene, they found that there was a presence of some nickel moiety, which is affecting the reaction, and therefore it is only stopping at the butene level and not continuing the chain. So this was all about today's session where we discussed about the Philip process, the Ogber process, different types of polymers based on their density and their different processes. Followed by that, we discussed about you will get whole session on the YouTube. The link has already been shared with you guys. So the assignment questions, these are just uh, different types of questions that has been used. These are not exactly the same questions that you guys have to follow it up. They are there. They have been put forth so that you guys could get an idea how to solve the questions when they are being asked in the exam. So as I said, increasing order of the segmental mobility in thermoplastic, we considered 5 different types of the polymers. So based on the last 2 types, they are just the combination of these three. So we are having thermoplastic, duroplastic, and elastomers. So we have already read 2-3 times that which one is having more mobility. And we know that elastomers are having more mobility compared to the thermoplastic and the duroplastic. So this is the kind of question you can get. Now, then we were talking about elastoplastic exhibit which kind of hybrid properties. The name itself suggests that it is having a property of elastomers or thermoplastic. At low temperatures, this dominates, and at high temperature, this dominates. Then this is a question from your Ziegler-Natta catalyst also, that the typical molar masses of the high density that would range in less than 10 to the power 5 dBi. It can't be more than that and not even lesser than that range. So it's just a theoretical answer. Then it has been asked that correct order of the density in these three particular polymers classified based on the density. You already know the name suggests high density polyethylene was having up to 0.97. This is having up to 0.94 and this is having up to 0.925. Obviously the HDPE is more. So the HDPE is more, then LLDPE and then LDPE. Then we have seen filler process. What filler process does, it produces the high density polyethylene using the chromium catalyst. And that's the next question, that which catalytically active species that it uses chromium plus 2. We actually starts with chromium oxide, but it is not your catalytic active species. Catalytically active species is something which would be regenerated in the system. So plus 6 is not getting regenerated, it's the plus 2 which is actually regenerating. And that is the question, monomer of the nylon 6, which I have already covered in the session. Nylon 6 monomer from which the nylon 6 is being made, it's the caprolactam. But if it is being asked nylon 6,6, it has to be adipic acid and this diamine. So be very careful when you're answering any question. Nickel effect we have already talked about. It has been observed in the Offer process that it goes into the dehydroalumination where it releases the aluminum hydride compound. This also we saw that polymer molecular weight increases drastically at higher concentration. So conversion and molecular weight are constant to each other when we have chain growth. But when we have a step growth at certain conversion rate, it would shoots up the molecular weight. And if it is a linear, that is a leaving polymerization. So out of the four options, we have the right option as step polymerization. And the last process, which is again a theoretical one, the polyethylene polymerization process that is carried out in fluid bed reactor that happens, that calls us unipole, because all these Ziegler-Natta we have already studied, Phillips we have studied. So none of these three processes act in fluid bed reactors. They occur in the different reactors having the heterogeneous catalyst. So I hope I have made you understand the things in very short span of time. If you have any question, you can just ask. You will get all the PDFs of this session and YouTube link also. You can go and watch the same at any point of time. If you still feel any question, you can come back in next live session. That would be in next week, Saturday from 6 to 8. Is there any question? Reference books that are already there in the presentation right now. I don't have the access to those presentations, right? You can just you can just log into your NPTEL site and there the reference books have already been given. And if not, then I will share in the next session. Whatever the books that professor has recommended, you have to use that one only, because that would give you maximum examples and proper mechanistic details also. So all the details you will get it there in NPTEL site. Yeah. Apart from that, is there any other question? Okay, so if not, I thank you for joining the session. Please feel free to ask questions, and if you don't understand anything, because you have joined a little late, I had to rush within this time. So I would request you to just go through the videos, what professor has taught, and the questions that I have shown over here. If you still feel any query or something, you can just mail back to me, or you can ask your question in the next session. Uh, Thank you very much for joining. I'll just end up the session now. Thank you.